we are going to be looking at system reliability and availability modeling. System reliability and availability modeling. That's what we're going to be looking at. It's not going to take our time. So first, the objectives is that by the end of the lesson, you should be able to analyze system reliability and the availability. And when we talk about the word analyze, we are simply talking about computing it, okay, in numbers. So you can see for sure that this system can last for 1,000 hours, 50 hours, and so on and so forth before it fails. Number two, should be able to model systems reliability using mathematical tools and then differentiate between system reliability and the availability. You should be able to explain the difference between system reliability and the availability. Now, we'll go by definition. Reward reliability is defined by the probability that a system will perform its intended function without failure over a specified period under certain conditions. So I want us to look at the keywords. Number one is the possibility, that's the probability that a system will perform its intended function. It's possible that a system is up, but it's not performing what it is designed for. Okay, so we want a system that will continue to perform its intended function, and then without failure, then there's a time frame that is attached to it, and there's also a condition that's attached to it. Okay, so we say reliability is defined by the probability. That's a possibility that a system will perform its intended function without failure over a specified period and under certain condition. This is reliability. In other words, we can rely on this system to perform for 1,000 hours before we can talk about maybe refilling the tank, okay? Or maybe let's just say a printer, that you bought a printer. You are saying that this printer, the print cartridge is able to at least print up to 1,000 sheets or pages of a paper before you talk about refill. So that's to the extent that we can rely on that system. In other words, if we get the system and we needed it to function for 30 hours and the the reliability is 1,000 hours, then we won't have anything to fear. Okay. Now, the second thing that we are looking at is availability. We say it is defined by the proportion of time that the system is operational and accessible when needed for use. You know, it's possible you are coming to print and then the thing is not, your printer is not up, and then the question is, for how long can this system be available for me? For how long can it be available? In other words, we are not talking about the physical presence of the system. We are talking about being able to make use of it when we need it. So this availability is influenced by how often the system fails, and then how quickly it is repaired. So you now see that there are other things that is attached to the availability of the system. One is the reliability of the system. That's how often, the probability of the time we can use the system. And then another thing is, if the system perhaps fails, how quickly does it recover? Or how quickly does it recover? Okay, So we say that why reliability focuses on preventing failures, availability both focus on failure occurrence and the system's ability to recover from such failure. So that's what availability is all about. Okay. So it's possible that a system, the availability of a system may be, let's just say that this system may be available for 1,000 hours. But if it fails, it may take another 50 hours to bring the system back to operation. And then there's another system that is available for only 300 hours. But if it fails, it may just need only 20 minutes to bring it back to work. Now, when you consider these two conditions, you know which one to pick. Okay. Now let's continue. Let's look at definition, system reliability. We say that it is the likelihood, the moment we mention the word likelihood, what comes to mind? Probability. All right. So systems reliability is the likelihood that a system, component, or service will operate without failure over a given period of time. So it can be expressed as this. So we have R of T is equal to the probability that there is a time that exceeds the present time of reference. All right. Now, what does that mean? RT is the reliability function at the time T. That's the time we are referencing from. And then PT is the probability that the system's time to failure, T, exceeds at least the present time when we are referencing from. Okay. So we say that reliability is given by the probability that T exceeds, the capital T exceeds the time of reference, which is the small t. Now, we now need to talk about the failure rates. The failure rate is represented by lambda. As represented by lambda is a key measure in talking about reliability. How often it fails, the system fails, is a thing that we will not take for granted when we are dealing with how reliable a system is. So it defines how often failures are likely to occur, and it is used in exponential distribution models, which is common in electronic systems. So we have the probability density function for the failure time f of t in system with a constant failure rate written as this. Now, when we look at this, we see that the failure rate is both a coefficient of the time and that of the exponential function here. So the reliability function R of t for exponential distributed failure time is given by this formula. And as a matter of fact, when we talk about the exponential function like this, we are talking about a decay graph. A decay graph. Let me just see if I can write something here. Okay, so what we're talking about is if you have a graph like this, so you can have the graph like this. All right. This is the arrow, or you can have it moving this way. So whichever way it is kind of starting from a high point and then it is going down. So maybe at the point that the system starts, it starts at this point, and then as time goes on, we see that the time it will take for that system to fail is drawing closer and closer. Okay, so that is what we mean. Sorry. So that is what we see, or rather what we talk about when we talk about this kind of function. It produces a graph like this. So the reliability of a system decays as the system is in use. Are you with me? Okay. Now, the lambda is the constant failure rate, meaning that it constantly decays. YT is the time period of interest. So as time goes, we see that the failure rate, the reliability of a system decreases. So if you get a new system, yes, you can start using it, and after a while, you will notice that the battery is no longer lasting for 4 hours, for instance. Maybe after a while, the battery will start lasting only for 3 hours, and so on and so forth, until your laptop becomes a television that when you put it on, and the moment NEPA takes light, it will go off. All right. So know how to get back this thing. Sorry. So the next thing we want to discuss about the time, mean time to failure, because this is going to be a very good function for us to use in making our mathematical computations. So mean time to failure is actually a measure of reliability, and it tells us the average time. Of course, you know that when we talk about mean, we are talking about average. Now it tells us the average time a system operates before it fails. Now for systems, before it fails, okay? So this is what it is like for system with an exponentially distributed failure time, okay? So we say that MTTF is equal to 1 over lambda. And remember that lambda is actually the failure rate. That's talking about how many times the system fails within the specified period of time under that we are observing the system. So look at an example. We say if a system has a failure rate that the time it takes to fail, or rather the failure rate is 0.001 per hour, okay? Now, the MTTF, that is the mean time to failure, is going to be 1 over that lambda, which is failure rate, and is going to give us 1,000 hours. So it means that when we start using the system, we expect the possibility of that system experiencing failure around 1,000 hours. Now, we are not saying exactly that the system is going to fail when it is 1,000 hours. Okay, what are we saying? We are saying that the average time that this system is going to work is perhaps going to be 1,000 hours. What does that tell us? That in the batch of those systems that were produced, it's possible that maybe some may start misbehaving at 900 hours. Some may start misbehaving even at 800 hours. And then you will still see somebody that's bought a batch, bought from the same batch that was released, that the system had served for 1,500 hours without failure. So what we are saying at this point in time is that our calculation is just giving us the mean time to failure for that system that we have developed. Okay, now before we proceed, there is need for us to look at reliability block diagrams. Now, what does this mean? You know, when you studied your physics, there is something that we did when we started talking about resistors in series and resistors in parallel, and capacitors in series and capacitors in parallel. That's the kind of thing that we see here, because we had talked about how to build robust systems, and we talked about building triple modular redundancy. In fact, building redundancy into the system, building failover systems that we switch from one component to the other when a component experiences failure. So we are going to look at a block diagram that typifies this. So the reliability block diagram is actually a visual tool that represents the functional dependencies of the components in the system. So some of these components can be connected in series, and some of them can be connected in parallel, or even a combination of this. And the purpose of this overall arrangement or architecture of this system is to improve the reliability of the overall system based on how the individual components of that system interact. Now, let's take a look at a simple computer system, for instance. This just a block diagram, like we said. Now, you know that because of what is happening in your processor, it runs a good number of cycles per seconds, all right, or per hour, depending. So when you talk about gigahertz processor, it means that it runs how many billions of data clock cycles. Now, those repetition actually makes the system to heat up. So inside of your hardware systems, you will usually notice that around the processor or on top of the processor is a cooling system, heat sink, kind of heat sink, okay? And then the heat sink, after the heat sink, you are now going to see a fan that is directed at it. And what is it doing? What it's doing is that as the heat sink is absorbing the heat from the processor of your computer, the fan is blowing away the heat. So if you look at the back of your computer, you usually see the system. You usually notice that hot air is coming out of it. All right. Now, this same thing happens in your system, in your car system, and you notice that your radiator system is actually connected before your engine. And what happens? Water is put in the radiator system, and as the engine is working, through the radiator, the heat is being sucked out of the engine and is being blown. So you see the radiator fan inside of your car, your bonnet, usually attached to that place. So if anything happens to your radiator fan and it is not blowing again, you will notice that the temperature in your system, in your dashboard, will immediately rise. Now, because you don't want that temperature, and if the temperature rises, the top gasket of your car is going to burn. But forgive me if you don't know much about cars. Now, this is the same thing. This is the same arrangement that is inside of a system, okay, your computing system. And these systems are programmed, because some of you may be thinking that I'm talking about hardware here, where you are talking about software engineering. These systems are programmed to supply power, to supply help to each other. For instance, this fan is meant to blow away hot air from the cooling sink, so that more more heat can be absorbed and pushed away from the processor, so that your processor doesn't get destroyed. All right. Now, there's the possibility these two fans are now arranged in parallel, like you likely know in your basic physics. What does that tell us? That there's the possibility that this one fan will get destroyed on the process. Maybe the coil that is powering the fan may get destroyed, and then this one will suffice for a moment. Okay, so it's possible to have maybe up to 3 or 4 fans around the processor, depending on the processing speed and what that system is meant to achieve. And you have done, we are talking about fault tolerant computer. You have actually made this arrangement deliberately so that you will protect this processor depending on the value of this processor. And of course, you know that in computing system, the moment the processor gets destroyed, the system will not work no matter how. Now, This system may likely work if one fan is not blowing, but not this. So the moment the processor is destroyed, you will notice that the hard drive will not work. Now, when you look at this, you notice that the power system is connected in series with the fans. In other words, the fan, without the power system, the fan will not work. All right. Now, this one is also connected in series with this, but these fans, because they are doing the same thing, they are connected in parallel, and we wouldn't want to destroy, rather because of what we have here, we want this to remain, okay? Maybe if one gets destroyed, let other ones continue functioning until we fix this one. So this is building tolerance into the computing system. Now, I've mentioned that this block diagram shows series and parallel, or a combination of both. So the example that I gave here talks about this one is actually a combination, because while processor and hardware are in series, these two fans are in parallel, and together these two fans are in series with the entire system. All right. So we have a combination of what I have just mentioned. All right. Now, when we talk about series connection, in series system, all components must function for the system to be operational. I've made this statement in passing, right? The reliability of the series system is now the product of individual reliabilities of the components that made up the system. Now, if we can depend on this system, if we can rely on this system, it is because the total reliability we can place on this system is the product of the reliability on the hardware with the product of reliability of the processor, with the product of the reliability of this arrangement, and then the product of reliability of this particular power supply. Now, if this system gets destroyed, what happens is that we will start with the power supply in troubleshooting it to know what actually happened to it. Because the moment we discover that the problem is here in the power supply, we are going to be able to reactivate all other ones. All right. Now, if we want to talk about parallel systems, that means in parallel system, at least one component must function for the system to be operational. Just like I mentioned here, that it's possible that we can have this fan destroyed, and then this fan will take over the function and still be working. Okay, so the reliability of a parallel system is shown here. So we have the number of components, we multiply the number of components or whatever, 1 minus R1, the reliability of the first component, multiplied by 1 minus the reliability of the second component, and so on and so forth, depending on the number of components that are in parallel. All right. And then when we get the the value of the computation of this, we now subtract it from 1. Are we together? We now subtract it from 1. So without much ado, you know that even if I did not put a bracket like this here to tell you, the mere fact that there's multiplication here and there's multiplication along the line here tells you that because of board mass, of course, you know board mass, because of board mass, that we are going to first of all deal with this side and then subtract it from this. All right. Okay, so that is it. Now let's look at, we have talked about reliability. We now want to look at availability. Now, what is availability? We say that it is a measure of the proportion of time a system is operational and ready for use. It is the proportion of time that a system is operational and ready for use. That means this system is available for you to use. Now, mathematically, availability can be computed as this. Okay, we can compute availability using this formula. Now, what does MTTF mean? It means the mean time to failure, whereas it means the mean time to failure, whereas the MTTR is the mean time to repair. Now, when I was discussing in the previous, in the beginning stuff, in the beginning slides, I told you that availability talks about the time to failure as well as the time to repair. Okay. So we will now see the two components here. So we see availability equals to the mean time to failure over the summation of the mean time to failure plus the mean time to repair, the time it takes to repair. Now we have types of availability, and this is for your noting. We have inherent availability, which considers downtime related to repair actions only. And then we have operational availability, which takes into account all downtime, including maintenance and logistical delays. Okay, so this is for your noting. Now, another component that we want to bring into availability is mean time between failures, okay, which is the measure of the reliability in the context of both the uptime and the downtime, okay? So in between the time it has been operational, what is the availability like? And when you consider it with the time the system takes to come back to operation, even when it has failed, that is the mean time to repair. And this brings us to the illustration I gave previously when I made mention about a system being operational for 1,000 hours, okay? And if it fails, it will take about 50 hours to recover. And then a system that is operational for about 200 hours but takes about 30 minutes to come back. Now, if you have the understanding of this thing, you will quite know which system to choose per time. So availability, as we have discussed, so from this place, the mean time between failure is actually the summation of the mean time between, the mean time to failure and the mean time to recover. All right. So when we now talk about availability, can also be expressed in terms of MTB, that's mean time between failure, and the MTTR. Now, what does that mean? Okay, if we want to talk about availability in that context, talk about availability in the context of MTBF and MTTR, what are we going to say? That MTTF is going to be equal to MTBF minus MTTR. Okay, that's MBTF minus MTTR. Now, what it means is that from our initial equation, we are already going to do away with it, with this, that is mean time to failure. Now, what it means is that we can still compute availability when we are not given the mean time to failure. Are we together? Now, this is the main function, the main formula for availability. Look at our formula for availability here. All right, this is our formula for availability, MTTF. Now, if in a question we are not given MTTF, but we are given MTBF and the MTTR, we are saying to ourselves that the MTBF, that's the mean time between failure, is also a function of MTTF and MTTR. And so we can compute MTTF by subtracting MTTR from MTBF. So if we do that, what we are going to get is we are going to get MTBF minus MTTR all over MTBF minus MTTR, then plus MTTR, I hope you can get it here. So what we are going to get here, I'm not having my writing pad, but let me see if I can write. So what we are going to get here is going to be minus MTTR, then plus this particular MTTR here, okay? MTTR. So minus this plus this is going to cancel away. So we now have that availability also can be a function of MTBF like this, minus MTTR all over MTBF. So what am I trying to say again? That you may be faced with a question that did not show you MTTF, and you are required to compute availability, which is this. You are required to compute availability still there. And so what are you going to say? You are going to now use this, or rather find this by substitution, by subtracting MTTR from MTBF. Okay, the question shows how the repair time or increasing the time between failure improves availability. Now, if you now compute the example that I gave, what's the mean time between failure? Okay, we say, let's just say we have 1,000 hours, and then the time to recover is going to be what? Is going to be, if you compute it, I'm not sharing my entire screen, I would have raised the calculator. If we say that the time it takes, like what I said, that the other one is 1,000 hours, but the repair period is going to be 50 hours. All right. So if you now divide it by 1,000, what you are going to get is going to be 950 divided by 1,000, which is going to be probably 95%, right? This is it for that system. Okay. Now, the second system I described, I said 200 hours. Oh, sorry. I said 200 hours. But the time it takes to recover is only 30 minutes, which is 0.5 hours. Okay. Now, if you divide it by 200 hours, what are you going to get? If you have your calculator, you can help me. So what we have here is going to be 199.5, right? All over 200. So if you raise 199.5 divided by 200, can somebody help me with it? Okay, 199.5 divided by 200. So you notice that this one now is 99.75%. I hope this illustration makes sense. Now confirm if you are still following me. Let somebody talk, please.
We are following you, sir.
Okay, so these two illustrations that I've given now, you can now discover that although the mean time between failure of the second system is just 200 hours, but it takes 30 minutes to recover, you can now compute and analyze and say that that system is more available than the other one. Okay, so you can see for yourself. This is just the analysis we're talking about. Okay, I think I even have an example like that. So let's look at this example that we have here. We said if a system has the MTBF, if a system has the mean time between failure of 1,200 hours and MTTR of 200 hours, what is the availability? You now see this one minus 200 divided by this. You see the availability is 3.3%. All right. So that is it. Now, let's look at comparing availability with reliability. So we say that while reliability focuses on how often a system fails, that is the likelihood that that system will operate without failure over a given time period. Why reliability is focusing on that? Availability is considering not only the likelihood of failure, but also how quickly that system can be repaired. It measures how often the system is operational and accessible for use. Now, let's take, for instance, your mates are buying Toyota that every mechanic around you can work on, and you want to show off that you have money, you go and buy Tesla. Okay, so the Tesla may serve you, but you may discover that here in Nigeria, when the Tesla has issues, you may need to waybill your car to Lagos or maybe wherever for it to be worked upon. Now, that is the thing that you need to consider even when making purchases. All right. And also, when you are developing systems, you also have to consider this. Let's look at this example. A very reliable but slow, okay, system A is very reliable. And how are we saying that it's reliable? Because it has the mean time to failure of 10,000 hours, but slow time to repair of 500 hours. Okay, so it takes time for that system to be repaired. Now you see another system B, which is less reliable. The mean time to failure is actually 1,000 hours, but it's quick to repair. That is, the mean time to repair is 1,000 hours. Now, for system A, we can compute the availability as shown here, and we see that system A is 10,000 divided by 10,000 plus this is going to give us 95.2%. And the other one, 1,000 divided by 1,000 plus 1 is going to give us what? 99.9% availability. So you can now see that there are factors, the factors that can compare to availability of a system. And that is the mean time to repair. Is also a very important concept when you want to compute this. Okay, so you say even though system A has a higher reliability, that is longer time before it can fail, system B is available more often due to its fast recovery time. Now, some real-world scenarios. The understanding of the problem domain enables engineers to consider the necessary trade-off when designing systems for availability and reliability. Examples of reliability-focused systems include medical services, spacecrafts, reliability. We're talking about reliability. How can we rely on this spaceship, this spacecraft that we are launching there? How long is it going to stay there? Is it going to remain operational for some certain time, withstanding the weather conditions in that area? Those are the things. Now we talk about nuclear reactors that you don't easily enter into. Okay. Now, and you know that if this system fails, if this system fails, that failure can be catastrophic. So you see that it is not something to toil with. All right. Now, examples of availability focused system include web server. You know, you are developing a system for a banking service, and for 2 hours you are telling customers in queue that the service is not going, that this one is happening. Cloud services and telecommunication networks, where rapid recovery from failure is more critical than preventing the failure altogether. Okay, so you can now see that although there are systems that may be reliability focused, there are others also that are availability focused. Now, when you are employed to work on a system, these are the things that you need to have in your mind in order to develop not just a system that works, but a system that is available, a system that is reliable, and so on and so forth, a system that is able to recover from fault quickly. Are there things that you need to put in place to make failure not to be catastrophic? You are going to put it in place. So this understanding will make you not to just develop a website for maybe a fintech application, and then your measure will be it worked. No, it's not just going to be it worked, because if you have understanding of how needed or how available that people will want this system to be, then you will know what to put there. And then it will also, because when you are developing systems that are robust, the pocket of your client also will need to tell him that you are not playing. Now we have trade-offs in reliability and the availability design. Which one do I prioritize? That is it. Costs. Number one, cost versus reliability. Increasing system reliability often involves added costs, such as redundant components or higher quality materials. Okay. Then another thing is complexity versus availability. System that is designed for high availability often include mechanisms for fast recovery, but these things now will add complexity to the system design, which will also lead to extra costs, even maintenance, and even more error prone. So you have to have this in mind. And so when you are now discussing business with your clients, you are bringing some terms to make the person know that you are not just going to design an it worked system. Okay. You are designing a system that will both be reliable and available. All right. Okay, this is the end of the class presentation. Now we can see some sample questions, more like what you may expect in your examination. So let's look at, I have 7 sample questions. Well, we are going to look at maybe 2 or 3 because of our time. Okay, question 1 says you have a system with 3 components that are connected in series. The reliability of each component has been computed as follows. And the question is, calculate the overall reliability. And I hope this one is a simple one, because it's just going to be the product of the individual reliabilities of each component. So we see the computation here. This is the formula, and this is the computation. All right. And it gives us 90.1%. Now we have question 2. A device has a failure rate of lambda equals 0.0005 failure per hour. What is the mean time to failure for the device? The solution is just 1 over lambda. So you have 1 over this, giving us 2,000 hours. Now you have question 3. I hope all these things are cheap. Yes? Hello? Please confirm that you are following me. Am I talking to myself?
We are following.
Is it confusing? Is there a place that you are not following?
Sir, I can't see the question on your screen.
You are not seeing my screen?
Yes, I'm just seeing the question now. It just showed now.
Okay, see, of course, I will still send this PDF to you guys. Okay, so we are now in question 3. It says that a machine has a constant failure rate of lambda equals this, failures per hour. It says calculate the reliability of that machine for after 100 hours of operation. Okay, now what do we have? For systems with constant failure rates, we now see the reliability function given as a decay function here. And so we have E here to be, sorry, we have RT to be exponent of the lambda times T. So, and the failure rate lambda is actually 0.002. So it has 0.002 multiplied by 100, which is going to give us what? E to power minus 2 or so. And then you now find the exponent of that, which is approximately this. Excuse me. Which is approximately this. I hope my calculation is not wrong. So you can also compute and be sure that this calculation is right. Now look at the formula and then you implement it. Let's look at question number 4. I think that this, of course, these things are not too difficult. They are not difficult. A system has an MTTF, that's mean time to failure of 500 hours, and then mean time to recover of 5 hours. Calculates the system availability, and that is very cheap. Of course, you can see it here, 500 over 500 plus this is going to give you 99.01%. Then we have question number 5. A server has mean time between failures of 1,000 hours and mean time to recover of 10 hours. To improve availability, the MTTR is reduced to 5 hours. What is the new availability? What is the new availability? So what we're actually computing now is the new availability. So the first availability is simply what the 1,000 hours minus 10 all over 1,000 hours, which gave us 99%. Then when we now reduce the mean time to failure, to the mean time to recover to 5 hours, we now have 1,000 minus 5 over 1,000, which is now 99.5%. So you now see that when the time to failure is reduced, the availability increased by 0.5%, and so on and so forth. Now let's look at question number 6, availability for redundant systems. Now consider a system with 2 redundant components. 2 redundant components. Both must fail for the system to be unavailable. What does it tell us? Can somebody answer? Is somebody making an attempt? Now, if the system says that both must fail for the system to be unavailable, it means that those components are actually connected in parallel. Okay? It means that they are connected in parallel. So we have component 1 here. We have component 1 here. We have component 2 here. All right. So as the input comes here, if 1 is available, it will follow this side and then go to outside. If this 2 is also not available, it will follow this. So it means that if this one is unavailable, this one will go. If this one is unavailable, this one will go. So it says the both must fail. That means for this system not to work, the 2 has to be unavailable. Okay. Now it says that each component has a failure rate of this, okay, per hour, and a mean time to recover for this. It says calculate the availability of the redundant system. Now, what is the solution? It says for a parallel system with 2 redundant components, the availability of each component is computed as this. Okay, so we have the availability of each component. So when we calculate the first one, we have 1,000 hours. And then the availability of, what am I saying? Okay, this is the failure rate, all right? So from the failure rate, we calculated the mean time between failures. Sorry, mean time to failure as this. Now, for us to calculate the availability, we now calculate availability equals to 1,000 over 1,000 plus 2, which gives us this. All right. Now, because this thing is 2 components, the system is connected in parallel. Now, if you go back, you notice that I said it is going to be 1 minus the first component's availability times 1 minus the second component's availability. But since the availability of these two systems are the same thing, we now have a square of both of them here. Okay, so when we finish computing this, we just subtract it from this. So from what we have here, we computed this, subtracted from this place, and we got this. So when we now subtracted this from 1, we now got this. So the availability of the redundant system is now approximated to 99.9996%. Okay, so this is where we are bringing this class to a close. If you have any questions, you may quickly ask before we call it a day. You have any questions? I'm going to, by God's grace, make this video available because I think I recorded this class. So if you have any questions, can you ask? I've stopped the recording. So if you have